The Baeyer-Villiger oxidation is our last oxygen reaction that we're going to do in this class. It's not with the oxygen nucleophiles, simply because the Baeyer-Villiger oxidation is oxygen inserting into an aldehyde or a ketone between a carbonyl and a neighboring group. And so an aldehyde or ketone is actually converted to a carboxylic acid or an ester, right? If you have an aldehyde, it's converted to a carboxylic acid. If you have a ketone, it's converted to an ester. Let's look at this reaction mechanism. You use a peroxy acid, one of my favorite functional groups. Remember, the peroxy acid looks very similar to a carboxylic acid, but it has a peroxide bond in it. So that highlighted red oxygen is the most reactive oxygen, not only because it has the acidic proton, but it also has a peroxide bond, which is very, very reactive. That oxygen will attack the carbon of the carbonyl, kicking up the lone pairs onto our oxygen. And then we will do an intramolecular proton transfer between the protonated oxygen and the oxygen of the peroxy acid carbonyl. That shouldn't be too big of a deal for us to do an intramolecular reaction. Intramolecular proton transfers are not good, we'll see later on in later chapters, unless we do have 5 to 6 atom spacing, right? So we do need that proximity to be between 5 to 6 atom transition states. So here we have 5 member transition states. And so later on, we'll see where these reactions of intramolecular proton transfers might not occur because it's less than 5 membered transition states. 5 and 6 is always great because remember, those are the most stable cyclic structures. And so that's where we're hinting towards this 5-membered ring transition as a more stable approach. Okay. And then we get a rearrangement. Oxygen from the ketone or the aldehyde relaxes back down, and we actually get the rearrangement of one of the neighboring groups, either the R groups or the hydrogen, whichever one of these. Let's highlight them. It's one of these two, right, that get rearranged, and they will pop over to the peroxy acid oxygen, the one that's still highlighted red. That will cause the detachment of the rest of the peroxy acid, very similar to epoxidation way back from chapter 8. So now we have inserted an oxygen in between the carbon of the carbonyl and one of the neighboring groups. Cyclic ketones produce lactones, which are actually really, really important for biology. For aldehydes or unsymmetrical ketones, the rate of migration is this. Usually a hydrogen will migrate first, it's the smallest. Then a tertiary, primarily the reason for the tertiary moving is because of its carbocation stability, all right? Secondary, and then a phenyl group. pH is a benzene ring, phenyl, and then primary, and then methyl. So use this trend to determine the regioselectivity, who's going where, okay? We can see that trend in a couple of examples. Let's just look. We have this group, or the primary, essentially, it's a primary on the right-hand side versus a tertiary on the left. Tertiary, primary. Which one is better? The tertiary. So Baeyer-Villiger oxidation will take and put an oxygen there. Same thing, we have a phenyl versus a hydrogen. Hydrogen is most likely going to move. So this is a great way to make carboxylic acids from aldehydes. If you have an aldehyde, you're always going to make a carboxylic acid with the Baeyer-Villiger oxidation. Last up in this chapter is synthetic strategies. We're going to practice with trying to do all of these reactions together. Now, biggest thing that we can kind of think about in this chapter and what's new to add to our toolbox is that we have new carbon nucleophiles, and those carbon nucleophiles are super important in changing the carbon skeleton. So remember, these are the two questions that we want to ask ourselves when we are looking at a reagent or a starting material and looking at how it's linked to the desired product. First step, is there a change in the carbon skeleton? Do we add or subtract things? And I really want to mention here that in all of these reactions that we learned in chapter 18, the carbon nucleophile ones, Grignard's, cyano groups, or the Wittig reaction, these all change the number of carbons in our group. So very, very important to remember those. And then the second question, is there a change in the functional group? Well, gosh darn it, I hope so. That's a synthesis, right? So these two reaction questions are should be at the forefront of our mind. The first one, new stuff, Grignard's, the cyano group, and the Wittig with the phosphorus ylide. We should be able to make a list of these products that can be made from aldehydes and ketones. I really highly recommend pausing to see if you can really come up with all of these lovely interconnections. We will practice them in class, obviously, but looking at carbon nucleophiles, hydrogen nucleophiles, nitrogen nucleophiles, sulfur nucleophiles, and oxygen nucleophiles, we have a variety of new reactions with our aldehydes and ketones that we can interconvert things from. Okay, so take that moment to go back and rewatch if you need to. Just to remind ourselves of spectroscopic analysis, things from chapter 14 and 15 are still really, really important for us, and you will still see them throughout all of our chapters in this semester. The carbonyl creates that strong C double bond O stretch around 1700. Remember, resonance provides less carbon-oxygen double bond character. And so usually we see a lower wave number for those carbonyl compounds that are conjugated. But again, aldehydes also give that weak peak around 2700 to 2800 centimeters to the -1 for the CH stretch. So really important to start thinking about what differentiates ketones and aldehydes in our IR spectrum. Here's just a good one to kind of remember. Not only for an aldehyde will you see the carbonyl peak, but you'll also still see the hydrogen of the aldehyde stretch around 28 to 2700. So that's what it would look like, just in case we forgot. Proton NMR is still important, right? So when we're thinking about a typical alkane, the methylene group, CH2 group, starts at around 1.2 ppm. Remember, when it's adjacent to a carbonyl, we add 1, right? Plus 1 ppm to appear more downfield for those methylene groups. So know the difference between the protons next to a carbonyl. Also, the aldehyde proton itself appears around 10 ppm. Carbonyl carbon produces a weak signal around 200 for the carbon-13 NMR. All right, so if we're thinking about carbon-13, again, yes, the adjacent carbons will be shifted more downfield that are right adjacent to our carbonyl, but the actual carbon of the carbonyl appears very far downfield at around 200 ppm. And here's our review of reactions, okay? So when we're looking at these reactions, we've learned quite a few this chapter. I would highly recommend concept mapping these and creating a chart for yourself so that you can do an overview of carbon, sulfur, nitrogen, hydrogen, and carbon nucleophiles.